Welcome to RC Circuits Differentiation. All right, with anything, whenever we add a new subject here, we want to try to define the subject. So differentiation is a measure of rate of change. That's from the Bell Book, page 56. So there's more than enough time for the capacitor to charge or fully charge and discharge during both the pulse width and the pulse space time. We're talking square wave pulse theory. So the pulse width and pulse space are greater than 5 tau, and when the RC is less than 1/10 of the pulse width, the capacitor is charged very rapidly. Only a brief pulse of current is necessary to charge and discharge the capacitor at the beginning and end of the pulse. The resultant waveform of the resistor voltage is a series positive and negative spike at the pulse leading and lagging edges respectively. That's also from the Bell Book. Okay, so we know that RC is equal to tau. We know that in a 50% duty cycle waveform, the pulse width will be equal to the pulse space. We know that the pulse width is the time on, and that's the time that the capacitor is going to charge, and that the pulse space is the off time, the time that the capacitor is going to discharge. Now, for differentiation to occur, we need RC to equal the pulse width divided by 10. And we can rewrite that equation and say that the time of either pulse space or the pulse width, that time for the pulse is going to be 10 times tau. So there's lots of time to charge and discharge. We've got more than enough time to fully charge and discharge during each pulse width and each pulse space. So here's an RC circuit where the output is taken across the resistor, and that is the standard circuit for differentiation. And we've got three different waveforms. We've got waveform A, where tau is equal to 10 times the pulse width, which this is not a differentiator. And you can see that basically the capacitor is just discharging just a little bit and then just charging just a little bit. So the main part of the waveform is getting to the resistor. And actually that's the formula for an integrator, but for an integrator we would switch the position of the capacitor and the resistor, and then you'd have that average voltage across the capacitor. So it's not a differentiator. RC equal to 10 times the pulse width is not a differentiator. It's actually an integrator. The waveform B. So now we can see the capacitors charging and discharging, but we see that it's just about getting to like 63%. It's charging and discharging. It's not discharging all the way. And so we know that we can see it says that RC is equal to pulse width, so you know that the RC is equal, the time is equal to 1 tau. So that makes sense that it's 63%, but it's not all the way discharged and it's not all the way charged. So it's also not a differentiator. We're not getting the spikes. On the next waveform, waveform C, we can see that we've got our differentiator formula where RC is equal to 1/10 times the pulse width, right? And we've got plenty of time now for the capacitor to charge rapidly and then discharge rapidly. And so we end up with those spikes across the output, the resistor, and we're looking for, basically, if you think of a differentiator as looking at the input signal, the square wave, and wanting to like highlight where change is occurring. And so that's what those spikes represent, is quick changes on the input.